I'm very pleased to have Andrei with us. He's a PhD student at the University of Yash, and he has been studying formal methods with a keen interest towards security, and that's what connects into this workshop. And yeah, please take it away.
Thank you so much for the introduction. Please excuse my voice. I have successfully managed to catch a cold. As mentioned, my name is Andrei Mogage, and I'm a PhD student since 2019, studying under the supervision of Professor Doran Canu at the Faculty of Computer Science from the University of Alexandria from Iași, Romania. We concentrate our effort on combining formal logics and cybersecurity. I'm also a security researcher at Defender since 2016, where I specialize on ransomware threats, more specifically ransomware analysis, forensic investigation, and where possible, the development of decryption tools. For today, I want to show my current work and my PhD, which involves enhancing malware analysis through the formalization of specific events of action that a malware may take. Our first motivation is that we've noted there are multiple cases where an analyst or a researcher is not actually interested in getting an overall picture of what the malware is doing, such as from a sandbox report or a debugger or some other form of analysis. So we may be more interested in just finding out if a malware has a specific capability. Does it steal data? Does it inject code? Does it perform keylog activities and so on? So first of all, we want to quickly check possible capability. Second, there are instances where we get that quick response. Such, as you can see on this snippet from a sandbox report, there are some specific information, and this report has been also enhanced with static analysis results. But they are more like an educated guess. They are not actually concrete. They don't have any concrete evidence. So we want to quickly verify capability, and we want our verification to be done. So in this regard, we propose taking-based logic, or EBL, that is actually based on the linear temporal logic on finite traces. So we want to express the action that an application takes as events that occur through time, and we base our analysis on Windows binary. So they either end at some point, they end their execution at some point, or they reach an infinite loop and report it will stop. The syntax of TBL consists of two main categories: behavioral pattern, which actually describes the events that the application may take; the capability pattern, that are more complex and describe a wider array of events that lead to a particular capability; and the rule which relate to the behavioral pattern is the capability pattern. Also, as the name suggests, we make use of state analysis. That is a powerful technique that allows us to observe and monitor the flow of information through an application. So we have a set of state sources, some sensitive information that we want to follow, and any other information elements or data that is computed from or derived from these state sources will also be taken, and we can follow it throughout the execution. We borrowed the logical connectors and temporal connectors from elsewhere on finite traces as well. So we have the same logical connectors, but we only use the next operator, the next connector, because we want to express that an event is followed immediately by another, but we have no use for other connectors such as globally or until, due to the way we express these events through time. However, there are instances where we want to express that an event A will take hold, and then after an arbitrary number of states, we'll have another event B that will also hold. This connector cannot be encoded through LDL or finite traces just using one formula. So we either need multiple formulas, or we have to enhance it with fast operators, such as we can say A is in the path of B, B is in the future of A, and there is an arbitrary number of states between them. But that would complicate things, and we want to be able to create a solution that may be used by multiple users that have no actual knowledge of formal logic, formal method. So we needed to keep it as simple as possible. To provide you some examples, first we have an atomic pattern, also known as a fact, and since we also use state analysis, here we have an example where a symbol T has been introduced as part of a stated element. We also have a behavioral pattern which combines facts and logical connectors and temporal connectors. So here we can say that A, which is an API, is a tailed source. Therefore, the next step will be to insert a tailed symbol for it, and then much later stage, we'll have that same symbol T propagated to the API B. In short, we can say that the output of A has been propagated to the input of B. And also we have a capability, which, as I mentioned, is a more complex behavior. So here we can say that an application has the capability of reading a file's contents. Another prerequisite is the tainted trace. So through the process of tape analysis and what's called permanentization, we create this tainted trace that consists of a set of instances of atomic pattern and represent various taint operations according to the taint sources and the taint policy. Here we can see that we have some API that represent taint sources such as create file virtual log. Therefore, we have the symbol we wanted to introduce for them, and the much later stage, those symbols will be propagated to other APIs such as read file or crypt encrypt. And of course, we have the TPL rules, which relate the behavior pattern and the capability pattern. So if you have this rule and the tainted trace, the behavior pattern is satisfied by the tainted trace, then we may safely assume that the application has the capability we've just mentioned. And this is actually the main key of our solution. In this example, we have a rule. So the left side of the rule is a behavioral pattern, and we say that we have this API create file followed by an insertion of a taint symbol. At a much later stage, that symbol is propagated to read file. So if you have a trace that satisfies that behavioral pattern, that application is able to read files. And as a side note, the Windows API create file is also used to open files, depending on the flags provided as arguments. To put our theory to use in implementation, we implemented into two different binary implementation frameworks, Intel Pin and COBI. We needed binary implementation because we wanted full control towards the application behavior and execution. We did not modify in any way. We just want to be notified each time certain instructions are executed, certain CPU registers or memory is updated, certain APIs are called, and so on. Intel Pin is a versatile and generic binary implementation framework, and it is quite useful, but it does not support highly complex, evasive malware that use anti-analysis tricks, so it will fail in some particular cases. Therefore, we also use COBI, which is another binary implementation framework, started during the PhD of a colleague of mine, Black Petru. And it was specifically crafted for transparency for evasive malware, but at this stage it does not support the 64-bit architecture, and therefore we end up using both of them depending on the context and the situation. In order to use our analysis solution, we need to provide a configuration here where we actually mention which APIs or code represent taint sources. So it will introduce taint symbols, how these symbols propagate to other registers or memory, and additional information that we want to collect. Of course, we have the rule which we want to test, and then we have the generated trace to the process of taint analysis as specified by the configuration. To provide some examples, here we have a rule that we want to test, and we want to verify whether or not an application is capable of deauthenticating a memory region, a payload basically, and then execute it. So we have this memory area, it is deauthenticated through decryption, deciphering, or some other computation, and then the malware will execute it. As taint source, we'll use these two instructions that are set by regular expression, and we will use regex because we want to catch all possible combinations of registers, memory, or constants. And we also use closed groups because we want to capture that element and provide it to some other predicate or to the following instruction. For instance, here The result of the XOR operation is used here as \1 on the next instruction, where you also copy the buffer in which the result is put, and we here on this predicate. The configuration also mentioned that anytime those two instructions are executed in an application, we will have two predicates introduced in the generated tree. Tainted T, so the symbol has been introduced, and drop the mem, and that memory is taken. Also, as a default behavior of our solution, each time a tainted memory is executed, we'll have another predicate inserted into the tainted tree, tainted code execute. Now that we know all this, all we have to do is create a rule that captures all this behavior. So we'll have an insertion of a symbol, followed to a propagation to memory, and then much later stage we have tainted code execute. Just a side note, we also use syntactic sugar, so these operators normally are binary operators, but there are instances where we have to change multiple predicates, so we just use this shorter version. So if we have a tainted trace of an application that satisfies that behavioral pattern, the left side, we may safely infer that the application is capable of payload obfuscation. Another example, here we want to verify if a malware is capable of communicating with the command and control server through a C2 communication. And as an implementation, we make use of basic Windows API for internet communication, such as Internet Open, Internet Connect, HTTP Open, HTTP send request. The first three of them are taint sources because their output is actually a handle to the connection or some configuration connection. So we make this chain where we propagate each output to another API until the last HTTP send request. So if we have an application that actually does this chaining of APIs, we may safely infer that the application communicates with the command and control server. Also, we provide an informal description as output, so any user may safely be informed what that capability is about. So it's much more descriptive. Also, to test our implementation, we've created 9 different tests. So we had 9 rules, as those two previously mentioned, and then selected 9 malware families and multiple samples per family. Due to lack of time and space, we only introduce here just one of the tests, but you can see here the results of that rule I just mentioned, this one. Again, samples from the dark side ransomware family, and then you can see also the hash for each sample, and here on this column, you can see the analysis duration. And the efficiency, to make it more faster, we stop the execution as soon as that capability has been expressed in that malicious application. However, we also compare to the native execution, but we did not want to temper the native execution to more in any way to influence it. So we had to let it execute until the very end natively. In any case, we can see that the overhead is quite minimal, and we have good results for all our synthetic tests. Okay, the implementation may sound good, but how does it scale to actual real-life use? Well, there were several cases where we had to perform forensic investigation for ransomware attacks, quite large scale attacks, networks involved. And we use this tool for a particular situation where we had a list of applications that we want to rule out or maybe to collect based on their certain capabilities. Does it exfiltrate data? Does it perform key logging? Does it encrypt data? Does it disable various Windows systems such as event logging or the user control and so on? So we used our solution and we had enthusiastic results. So it proved useful. Currently, we are 3 members that are using this tool, and once we expand our current rules, we'll have more rules and more versatile. We'll also expand the testing. And of course, given the range of large language models nowadays, we also had to try using artificial intelligence to make the process of creating rules much faster, to get some inspiration for possible capability. It also created a feedback loop because we had some initial information. We crafted some intelligent question for the model. We received some results. We then check the model more information, and then get more results, and so on, creating this feedback loop. To give you one example, we asked the model to provide us 3 capabilities of model that is capable of giving user information, and of course we use this list with concrete detail. Then we select one of them, the key logging capability, and ask which of them are actually, which APIs are necessary to create a keylogger. And of course, we choose the list. They are valid in those APIs, validated by the Microsoft documentation, and are actually useful in creating a keylogger. Naturally, the following step would be to ask it to provide us a C++ snippet which uses the Windows API to achieve that keylogger functionality. Now, for transparency, we use the Mistral model, and we deploy it locally, and that is why we actually put that such a question and receive the result without being blocked. Just a quick explanation, the main function is to use the settling of states API, which actually installs the hook function. Each time a key is present on the keyboard, that function will be called. What it does is uses message to translate the keystroke with character equivalent, and then it's written to the key locate file. So now that we have the entire behavior, all we have to do is create a rule. The behavior pattern is here. Also, as you can see, we use some predicates that verify certain parameters of API are as expected. In this case, we want this macro because it is used actually here. And if you have an application that performs that behavioral pattern, then it's a keylogger. We actually tested on some keyloggers and we have successful results. Now, as a side note, for each capability, there may be multiple ways to implement it. So I've just provided some examples of possible implementation for possible capabilities, but there may be multiple combinations of instructions and Windows APIs. Okay, I'm aware that there may have been a lot of information from different areas, but the main key points are this. We have an analysis solution that uses state analysis, linear temporal logic, namely our EDL, state-based logic, and malware analysis through binary instrumentation, and that is actually the ultimate goal. So we formalize every action that the application takes using state analysis. We produce that tainted trace, and then we have a rule that verifies if the behavioral pattern is satisfied by the trace, the application has that specific capability. All of our tests, both synthetic and real-life test experiments, have shown promising results, and for the future, we plan to first expand the current set of rules. So we have 9 rules, but there have to be many others in order to capture a variety of capabilities of malicious application. Next, we want to be able to use the capability of a rule, so the right side of a rule, in the left side of another, so we have a behavioral pattern, so we can chain these rules and then create rules that may capture malware types, malware families, or more complex capabilities. And of course, we plan to automate the process of creating rules, testing rules, and extract various information. Thank you for your time, and please let me know if you have any feedback or any questions.
Okay, so any questions? So in the meantime, people are thinking, so what kind of next challenges specifically thinking about the report that we have to write? So what kind of challenges do you think are ahead in this area of research?
Well, one of the challenges are actually describing capabilities that encompass a wider range of behavior patterns, as I just explained. Here we have a keylogger capability, and that is like an implementation. But we may use different APIs, we may use instruction level execution, and so on. So we need to find to create a rule that is both that on one hand encompass a larger way of implementation, but also does not add significant overhead. So we need to keep the execution as smooth and as quick as possible, and that may be challenging.
So any other questions?
Maybe, I don't know, Vasily, is in this context, I assume that since you are using, binary, traces, you are not interested in properties that will do transmission or
Repetition.
in the reactive system and you want that, something happens.
No, for now, we actually generate this ticket trade based on a concrete execution. And that trade generated according to the configuration. So the configuration says that only these APIs may insert the predicate into the trade. So we'll have a,
I mean, there are no properties that, I mean, with that characteristics that you may be interested in analyze.
I'm not sure.
I mean, you have that restriction, it doesn't restrict your interest, or
No, it's actually,
it says,
yeah, it depends on the user's interest of extracting that information. So it may vary.
Now, firstly, how many parameters did the Mr. model have that you used and how?
We use the visual 7 billion model. It was just an example. We didn't have a system strong enough to use Mistral, for instance, that uses 8 agents with 7 billion. We'll make more tests, but for now, it actually provided some good results with extracting capabilities and their possible implementation.
Okay, so let's thank the speaker again. Thanks a lot.
Thank you.